Lesson 73, factoring the difference of two squares. There is a special circumstance in which we can factor binomials, and that's when we have two perfect squares where one is subtracted from another. For instance, we might have x squared minus y squared. In order to factor this, both of these have to be squares, perfect squares, and they have to be a subtraction. There has to be a minus operation here, and I will show you why. When we factor this, we're going to have to eliminate two of the terms. Because we only have two terms here, we need to get rid of 2, because we're going to end up with 4, and the two middle ones will combine to make 3. So let me show you. If we factor the first one, we get x times x. If we factor the second one, we'll get y times y. Always, 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 this minus means that one is going to be positive and one is going to be negative. And what happens when you have that occurrence where you have the exact same terms, but one is added and one is subtracted in your two sets, you're going to get, let's do the FOIL method and I'll show you what you get. The first terms will be x squared. The outer term will be negative xy. I'm sorry. Negative xy. Could be positive. It just depends on where you put your plus and where you put your minus. Your inner term, which is plus y times positive x, is going to give you a positive xy. And then positive y times negative y, it's going to give you a negative y squared. That's your last term. When you combine that, these are opposites, so they cancel out. So all you are left with is x squared minus y squared. That is always, always the case when you have a perfect square for the first term and a perfect square for the last term, and they are subtracted. That is, you always have a positive and then a negative, and you put their squares in the first and the second position. So let's try that again, see if that holds true. We have 4p squared minus 25. Okay, 4p squared is a perfect square. Negative 25 is a 25 is a perfect square, but it has a negative and a positive. So we do two sets of parentheses. 4p, what do we multiply by itself to get 4p? 2p, correct? 2p times 2p is 4p squared. So we put 2p as our first term. And then we have 5 times 5. Well, one's going to be positive and one's going to be negative. When we go ahead and do our FOIL method, we do our first 2p times 2p is 4p squared. We do our outer 2p times negative 5 is a negative 10p. Let's do our inner. Positive 5 times 2p is going to be positive 10p. And then our last, positive 5 times negative 5 is a negative 25. So when we combine, these two cancel out every time. So 4p squared and negative 25. And that matches. And as you can see, one's positive, one's negative. So you can't put a square up here. That's not going to work. It has to be separate, positive and negative. Well, let's do another one just for giggles, I guess. M squared minus 16. Again, perfect square, perfect square. We set up our parentheses. We put in the first term, and then we put in a positive and a negative for the second term. We do our FOIL method to check. M times m is m squared. Our outer is going to be m times negative 4, so it's negative 4m. Our inner, positive 4 times m is positive 4m. And then our last, positive 4 times negative 4 is negative 16. These cancel. We have m squared minus 16. which is the same that we started with. Okay, that is how you do a perfect square minus a perfect square. When you see a problem that says factor the perfect square below, you're going to see a perfect square minus a perfect square. If this is a positive sign, you cannot factor it unless this becomes a negative. So this will have to change in order to make this factorable, right? Okay. All right. So let's begin. Let's do some practice, some example problems. 73.1. We can all do these pretty quickly on this one page. -4 plus x squared. All right, first of all, this is out of order because this is positive, this is negative, and this is a square, a variable squared here. So we need to rearrange it so that it's in the right format. It has to be subtraction, okay? So now we set up our parentheses. The perfect square of this is x times x. The perfect square of this is 2 times 2. One's going to be positive, one's going to be negative. Done. 73.2. 49 m squared, that's a 2, minus a squared. Both of these are perfect squares, and there's a subtraction. So we can set up our parentheses. The square root of 49m squared is 7m. You multiply those together, you get 49m squared. And a squared is going to be negative a, positive a. All right, if you want to check on this one, since it's a little bit more complicated, let's do it. FOIL method. 7m times 7m is 49. M squared. 7 times 7 is 49. M times m is m squared. Okay, our outer 7m times positive a is going to give us a positive 7am, right? Inner negative a times 7m is going to give us a negative 7am, right? And then our last, negative a times positive a is going to give us a negative a squared. When we combine, those cancel, and we're left with 49 m squared minus a squared, which is the same thing we have up here. All right, 73.3. Negative 36a squared plus 25y squared. Can we do this like this? No. We have the same thing that we had for 73.1. We have to rearrange it. So 25y squared. The first one has to be positive. The second one has to be negative. And they both have to be perfect squares. Now we can do our factoring. The square root of 25 is 5. Square root of y squared is y. So 5y and 5y. The perfect square of 36, the square root of 36 is 6. Square root of a squared is a. We're going to have a positive and we're going to have a negative. And that's correct. All right, 73.4. Last one. We have negative 36x, oh goodness, 6y4 plus 49a squared. All right, we can't do it in that order. The negative has to be in the middle. So we rewrite it, 49a squared minus 36x to the 6, y to the 4. Set up our parentheses. The square root of 49a squared is 7a. The square root of 36 is 6. square root of x6 is x3, and the square root of y4 is y2. It's going to be positive, and this one's going to be the negative version of that number. And that's correct. All right, so the things to check for when you are doing these is to make sure that these numbers are multiplied out to be these when you multiply them against themselves, and that you have a positive and a negative here. Otherwise, these numbers should be identical. All right, that's all there is for factoring the difference of two squares. That's all there is to it. Make sure you have the proper format of a positive square minus another square. That's all you need to do. All right, you have that format, then you can factor. Let's move on. 73b, probability without replacement. So far we've done probability with replacement. That means we have an urn or a box or whatever container we have, and we drew out a marble, we put it back in. We drew out a marble, we put it back in. Now all that did for us was it kept our total number of outcomes the same. This time we're going to try some problems where we keep the marble out after we draw it. So it's going to change the total number of outcomes we have. So for instance, if we have 3 black marbles in this urn and 5 white marbles in this urn, we have a total of 8 marbles, right? This is our total number of outcomes, or our sample set. So 8 is going to go on the bottom of our fraction. What we want to find out is if we have the probability, let's have a probability of drawing 2 black marbles, black and black. This is going to be with replacement. That means we put the marbles back. So we have 3 out of 8 marbles that are black. So we have a 3 out of 8 chance of pulling a black marble, right? So for our second draw, with replacement, so we put that marble back, we want another black marble. It's the same probability, 3 out of 8. So we would multiply those and we would get 9 over 64. That would be our probability for drawing a black and a black with replacement. Now if we have that same probability of drawing a black and then a black without replacement, that means when we draw that first black marble, we keep it out of the urn. That's going to change our outcomes. So the first time remains the same because all the marbles are still in the urn. So we have a 3 out of 8 chance of pulling a black marble. Okay, so let's say we pulled that black marble out. We kept it out. Now we don't have 8 marbles in the urn anymore. We have 7. And because we took out a black marble with the first draw, now we only have 2 black marbles in the urn. So now we only have a 2 out of 7 chance of getting a black marble. And now that is without replacing the marbles. Now we multiply, and that's going to be 6 over 56. And that's going to reduce to 3 over 28. If my pen will actually write for me. All right, 3 over 28. So that's how you do that. Each turn, you subtract from the top and the bottom, if applicable, whatever was drawn the first time, and then the second time, and then the third time, okay? So you see how that works? We just reduced our possible outcomes, our total outcomes by 1 because we kept the marble out. We took that marble out. So we had to say, oh, now we only have 1, 2, 3, 4, 5, 6, 7 marbles, and only 2 of them are black. So we have a 2 out of 7 chance of getting a black marble on the second draw. So if it helps you to draw a picture, do that, okay? Do that. All right, let's move on to our first practice problem, our first example problem. And we only have one for this, and that is 73.6. And we have an urn here. Let me draw another cute little fancy urn. It's a pretty sad looking little urn if you ask me. But anyway, our urn has 4 red marbles. So 1, 2, 3, 4 red marbles. And it has 7 blue marbles. So 1, 2, 3, 4, 5, 6, 7. We are going to figure out the probability that the first marble is a red and the second one is a blue, and this is going to be with replacement. Okay? So then we're going to figure our probability for the first one being a red and the second one being a blue without replacement. Okay? All right, so let's do that. So if we do have replacement, we're putting them back in. So first we need to know the total number of marbles. So we have 4 red and 7 blue. That gives us a total of 11 marbles, right? There's our little calculation right down there. So we want the first one to be red. So that's going to be 4 out of 11. You follow me? We have 4 red ones out of 11 total. We're going to put that marble back in there. So we still have 11 marbles because we put him back in. Now we want a blue one. There are 7 blue. So we have a 7 out of 11 chance. With replacement, we get 7 times 4 is 28. 11 times 11 is 121. So we have a 28 out of 121 probability that we will pull a red and a blue if we put the marbles back in. Now let's do the same thing without replacement. So the first one is the same. We have a 4 out of 11 chance that we are going to pull a red. So we pull the red with our 4 out of 11 chance. We keep the red out. We take it out. So now we have 3 red and 7 blue and 10 marbles, right? So now we want to draw a blue marble. So what changes? The 7 is the same because we didn't pull out a blue marble. We pulled out a red marble. So the 7 stays the same, but our total number of outcomes changes because now we only have a total of 10 marbles in the bucket or in the urn. So that's what changes with the second pull is the total number of outcomes. So now we do that same multiplication. 4 times 7 is 28, but now we have 110 as our denominator. And that could be reduced to 14 over 55. So 14 over 55 is the probability of drawing a red marble and then a blue marble after keeping the red marble out the first time. Okay? It's pretty easy. It's just a little bit of subtraction going on. And if you use your little calculation, little scratch marks down here, it helps you to see it as you go along. And you could do this for each draw. Let's say we wanted to do another probability. This is not in the book. This is just me. Of a red and a blue, and then another red without replacement, right? So we've already done the red and the blue up here, so we can just bring that down, right? We pulled out a red, all right? Now we pulled out a blue, and we want to pull out another red. So we pulled out the blue, so we have to subtract a blue. So now we are going to be down to 6 blues because we took a blue away, but we still have 3 reds. But we only have 9 marbles total. So if we want to draw a red, that's a 3 out of 9 chance. So 3 red marbles are left, and we have 9 marbles total. So that would be 4 times 7 times 3 equals 84 over 11 times 10 times 9, which is 990. And I believe we can reduce that by 2 at least. 84 divided by, let's see if we can divide it by 3. Yeah. So we can reduce 84 by 3 to 28. And we can reduce 990 by 3 to 330. I think we can reduce that again. So that would be, let's see if we can divide it by 6. So 84 divided by 6 is 14. And 990 divided by 6 is 165. So that's as far as we can reduce it. So that would be a 14 out of 165 probability that we could draw a red, a blue, and a red without replacement. And that's supposed to be a W right there. So you see how that works. You just reduce wherever you need to reduce when you take it out, and it affects the total and the number that goes under the bottom. All right. Awesome. So if you have any questions about this probability without replacement, feel free to contact me, text me pics. I'm always here. My phone may not be charged or my phone may not be with me, but I try to check it often. So text me a picture if you get stuck. Do your practice problems. Your practice problems are going to help you be able to solve these. And if you can solve all of your practice problems correctly, you know you're understanding what's going on. So I will see you in lesson 74. Don't forget to do your homework assignment.